In this video, we're going to practice finding the volume of solids that are created by revolving regions around the y-axis. So we've practiced revolving regions around the x-axis already, and this is going to be very similar, with just some slight changes. So let's consider this problem. Let R be the region bounded by y equals natural log of x and the y-axis between y equals 0 and y equals 4. Calculate the volume of the solid formed by revolving R around the y-axis. So as usual, we want to start by sketching our region R. So our region R is bounded by y equals natural log of x and the y-axis. So let's draw y equals natural log of x. Well, I know it has an x-intercept of 1, and it has this general shape. Okay, so that is y equals natural log of x, and then of course I have my y-axis over here, and specifically I'm looking between y equals 0 and y equals 4. So here's my region R in here, and I'm taking this region and I'm going to rotate it around the y-axis and create a solid in that way. So how would I find the volume of such a solid? Well, the way we've learned so far to do this would be by the disk method. So let me remind you of the formula for the disk method for rotations around the y-axis. Okay, so that formula looks like this. Volume equals the integral from c to d of pi times f of y squared dy. Okay, so here this function f of y just represents the function that's forming the boundary of your region, or you can think about it as your radius of rotation. So in my case, that's going to be this curve here, y equals natural log of x. So I'm rotating around the y-axis, right? So if I want to think about making little horizontal rectangular slices, if I picture rotating one of those slices around the y-axis, it's going to create a disk, and this pi f of y squared gives the surface area of that disk. Okay, so one very important thing to note about this formula is that everything is in terms of y. So that means that my integral should only have y's in it, and that my bounds c and d should be y values. So we've already mentioned that this y equals natural log of x, that curve forms this radius of rotation. But what we need to do is we actually need to take that function, and instead of having y equals a function of x, we need x equals a function of y, since we're integrating with respect to y. So out to the side, we can just take this y equals natural log of x and solve it for x. In this case, I'm going to have to do that by using an e on both sides. So I end up with x equals e to the y. So instead of writing y equals natural log of x, I can also describe this curve as x equals e to the y. So now I'm ready to set up my integral. I'm going to pull this pi out front. F of y in my case is this e to the y. And then I just need to remember to square that whole quantity. And my bounds need to be y values, and they're just going to be the y values that span my region. So in this case, my region R goes between y equals 0 and y equals 4. So those will be my bounds. And from there, I just integrate to solve the problem. So if I take it, well, first actually, let's rewrite this slightly as the integral of e to the 2y dy. So if I go ahead and find my antiderivative, the antiderivative of e to the 2y is 1/2 e to the 2y, and I'm evaluating this between 0 and 4. So if I plug in 4, I get 1/2 e to the 8 minus 1/2 e to the 0. I'm not sure what e to the 8 is, but e to the 0 is 1, so this is just minus 1/2. Okay, so I could write this as, if I wanted to, pi over 2 times e to the 8 minus 1. And that's the volume of my solid of revolution in this case. In this example, we're told to let R be the region bounded by y equals x and y equals 3x between y equals 0 and y equals 5. Calculate the volume of the solid formed by revolving R around the y-axis. So to start, we need to draw a picture of our region R so we can see what's going on here. So here on my graph, I've sketched in the lines y equals x and y equals 3x. And then we are interested specifically in the region between y equals 0 and y equals 5, which is up here. So here's my region R, and I'm going to rotate this region around the y-axis and form a solid by doing so. And I want to calculate the volume of that solid. So this problem is well suited for using the washer method. And specifically the washer method around the y-axis. Okay, so why is this a washer method problem? Well, my region here R, if I were to draw some rectangular slices here of the region, I'm taking this region and I'm rotating it around the y-axis. So in doing so, I'm taking an infinite number of little rectangles, tiny little rectangles, and rotating them around the y-axis. And when I do that, you can picture that I'm creating these washer shapes. So discs with a hole in the middle, or little donuts, if you want to think about it like that. So then what I'm going to do is I'm just going to find the volume of each of those washers and add them all up to get the volume of the whole region. So formula-wise, what does the washer method look like? Well, it says that the volume of my region is given by the integral from c to d of pi times f of y squared minus g of y squared dy. Now here, the important thing to realize is, well, one, that we're integrating in terms of y, but also that f of y represents the outer function, and g of y represents the inner function. Or you can think about it as the outer radius and the inner radius of your washers. So let's think about, in my case, what is going to be my outer function and what is going to be my inner function. Well, to figure this out, it's important to picture rotating this region around the y-axis. And you just want to think about, as you're rotating that region, which function forms the outside boundary of your solid and which function forms the inside boundary of your solid. So in my case, this line y equals x is going to form my outer edge, and this line y equals 3x is going to form my inner edge. So I'm pretty much to the point of being able to write my formula. The only thing that needs to be done is I need to make sure that I have everything in terms of y. So right now, both of my lines are written as y equals some function of x, but what I want is x equals some function of y. So let's convert these formulas. Well, y equals x is easy to convert. It's just itself. I can write it as x equals y. And y equals 3x is pretty nice as well. That becomes x equals y over 3. So now that I have these, I can go ahead and plug them into my formula. So I've put the pi out front. We'll put the bounds on in a second. So my outer function was y equals x, we said, and I'm just going to use the rewritten form of it, so use in terms of y. So this is going to be y quantity squared minus the inner one, which is y over 3, and square that quantity as well, dy. And my bounds need to be y values, and I'm told my region goes between y equals 0 and y equals 5. So that's my setup, and then all I have to do to finish this out is actually integrate. We can clean up a little inside first. So this is y squared minus 1/9 y squared dy. Or I could even write that as 8/9 y squared dy. So if I find the antiderivative, I'm going to get 8/9 times y cubed over 3, integrating from 0 to 5. So that becomes 8y cubed over 27 from 0 to 5. If I plug in 5, I get 8 times 125 over 27. Plugging in 0 is just going to give me 0, so I don't need to worry about that. So it looks like as my final value, I get the following. 1,000 pi over 27. And that is the volume of my solid of revolution.